Cycle 1, Lesson 4, Finite Differences and Leading Coefficients. This is a nice short lesson today. So, let's start with a new definition for you. Factorial. So, if you take a look on what's visible on my screen, you'll see 1 exclamation point, 2 exclamation point, 3 exclamation point, and so on. That exclamation point is actually a math symbol, and it's called a factorial. And it just means start at whatever number is there and multiply down to 1. So, for example, well, they have an example actually here, so let's use that one. So this example, 5 factorial, 5 exclamation point is read as 5 factorial. It means start at 5 and multiply down to 1. So you go 5 times 4 times 3 times 2 times 1. And that equals 120. So factorials grow really quickly. As the numbers get bigger, they go up really quickly. And so here's a few of the first few factorials, just so you can see what's happening. 1 factorial just means it's equal to 1. Don't have to multiply up anything, it's just 1. 2 factorial means 2 times 1. So 2 factorial is equal to 2. 3 factorial means 3 times 2 times 1, which equals 6. 4 factorial is going to be 4 times 3 times 2 times 1. So we could think of it like, I'll write that out, 4 times 3 times 2 times 1. But we just saw that 3 times 2 times 1 is equal to 3 factorial. So this part here, we already know is the same as 3 factorial. So I'm not suggesting that you would normally write it that way, but you can think about it. If you know you're getting 4 factorial, and you already know that 3 factorial happens to equal 6, as we do from just above, then we could do 4 times 6, which equals 24. So I'm not saying that we have to do it that way, but there is a connection. So then I could do it. It becomes easier to know that, okay, if I want to do 5 factorial, I don't actually have to do 5 times 4 times 3 times 2 times 1, since I already know that 4 factorial equals 24. Maybe I'll write it as 4 factorial first, though. Then I know that 5 times 24 equals 120. And that's going to be the same as 6 times 5 factorial. So 6 times 120 is going to equal 720. And then so on, right? Um, 7 times, well, let's not do this mental math way. I want to show you actually on the calculator anyway that you should have a factorial button on most calculators. So you can see over on the left-hand side of my screen, I'm hitting the button off and on, so maybe it's flashing for you. It says X exclamation point, X factorial. So if I just go 7 factorial, then it tells me that the answer is 5004. So I don't even need to do all this multiplication. I don't need to multiply everything out. It's 5004. 5040, not 5004. And 8 factorial would be 8 times that. But again, why bother when our calculator will do it for us? 8 factorial equals 40,320. So as I mentioned, they go up really quickly. So your calculator, check your scientific calculator, and you definitely need to have one for this course. I don't think I've talked about it in the lessons, but definitely you're going to have factorial buttons somewhere on your scientific calculator. Most people will have it as an actual dedicated button. For some people, it will be a second function above a different button. And for some very few set of calculators, you might actually have to go to a menu to find it. But every calculator, scientific calculator, will have a factorial button. So that's the first thing, factorials. The next thing we want to look at is finite differences in terms of polynomials. You know about finite differences. You know about first differences. or second, that's quicker to write it that way, or third, or fourth. Well, actually, you know about first and second, but there's also third, fourth, fifth, and so on. There can be any number of differences. And so that's going to come into play with polynomials as well. So think about what you know. Let's talk about, well, first and second for a second. You know that for a linear relationship, a linear function, first differences are constant. And they give us the slope, right? Think back to grade 9. You know from grade 10 that second differences are constant. And you may remember, well, definitely you should remember that if it's positive, your second difference is your parabola is going to open upwards, and if it's negative, your parabola is going to open down. You may also remember that the second difference is, whatever the number is, it gives you the stretch factor for your parabola. Well, like I said, we can have third differences or fourth differences and so on. So here's, for any type of differences, for second, third, fourth, millionth, here's what's true about them. They're all equal. They all have the same sign as the leading coefficient of the equal ones, the constant differences, will have the same sign as your leading coefficient in your equation. Remember, leading coefficient. I'm just going to write it this way for a second. Let's say we're looking at a cubic function. And I'm just going to use A, B, and C, and D for my coefficients. So my coefficients are all these numbers here, right? We got my terms. I got my x cubed, my x squared, my x, and then I got no x. I got a constant term. Those A, B, C, D they've highlighted in yellow are all coefficients. But this one is a special one. It's called our leading coefficient. Think again of parabolas. The number that comes first when things are in standard form tells us whether it opens up or down. So it's important to know about the sign of the leading coefficient. So for this cubic one that I've just sort of laid out for us here, the sign of what I've called A is going to tell us some stuff about our graph. All right? And finally, in the last bullet here, the constant differences are going to be equal to A, the leading coefficient, times n times n minus 1, etc., down to 1. Remember, n is the exponent, and so whatever our degree is, n is our degree, if we do a times n factorial, because that's really what this all boils down to, n times n minus 1 times etc. down to 2 times 1, that's just equal to n factorial. And so we get this, can be rewritten as a times n factorial. So the leading coefficients are going to be equal to a times n factorial. So let's make this clearer with an example, just one example before we're done. Here's a table of values for a polynomial function. We're told it's polynomial. We want to find the degree of the polynomial just from the table of values, and we want to know what the leading coefficient is. So, first differences. Have to start with first and then see. If the first differences all turn out to be constant, then we know we've got a linear function. Highly unlikely for this example, but who knows, right? So if we do the first differences, remember, we get the first differences by subtracting this number from this number. We subtract the first y value we come across from the second one we come across. So if we do 48 minus 153, we get negative 105. And then we're going to subtract 48 from 7. And when we do that, we get negative 41. So if I just go down and subtract all those, this is what I get. Clearly they're not constant, so it's not linear, so I move on to see if it's quadratic by getting the second differences. And again, now I'm going to subtract 105 from 141, sorry, not 141, just negative 105 from negative 41. Now you have to be careful about the signs. Literally that's going to look like negative 41 minus negative 105. These two negatives are going to combine to give a positive, so it's simplified to negative 41 plus 105. So actually these differences are going to end up being positive. The difference between them is positive 64. And then negative 7 take away negative 41 is positive 34. And again, you can already see they're not constant. It's not going to be, second difference is not going to be quadratic, but we have to keep going. I'll get 4, negative 26, and negative 56 for the second differences. We just keep going until we hit something that's constant. We know they're going to be constant at some level because the question tells us that it's a polynomial function. There has to be some level where they do all become constant. And so for this next one, 34 minus 64 is negative 30. 4 minus 34 is negative 30. Negative 26 minus 4 is negative 30. Well, this looks promising, doesn't it? Negative 56 minus negative 26 is negative 30. Okay, so we have a winner here. So these are our constant differences. There are third differences in this case. Let's just call them D. It's supposed to be a D to make things easier. And if we go back to that last bullet there, we're told that D is equal to A times n factorial. D equals A times n factorial. So that's going to be helpful because now we can find out what A is. Because this question is asking us to find two things. It's asking us to find the degree of the polynomial. And so we've just found the degree. The degree is third degree. Third degree. Okay? And it also asks us to find the value of the leading coefficient. And so that's A. So I have to find out what A is. So D is negative 30. Right? We got that from our table of values. A is what we're finding, and n is 3. I know that now because n is the degree of the polynomial, and we've determined that it's third degree. So A times 6, then I can divide each side by 6 to get rid of it on this side. And I get negative 5. And so that would be the value of the leading coefficient. So in other words, if I was to write out the equation for this polynomial, I don't know what it is, but I do know it's going to begin with negative 5x cubed, because I've got the leading coefficient, and I've got the degree, and then there could be some other terms. There could be a squared term, there could be a constant term, and there could be a linear term, and there could be a constant term. But this part is all unknown to us. That's not anything that we can figure out from this part.